All right, so we're going to go through this mass spec review video as fast as possible. I'm afraid it's going to be long, so I'm going to try really hard to stay on topic. So here we go. Question number 1. We are asked for empirical formula. So this is a nice little bit of stoichiometry review. To find empirical formula, we're going to divide our percentages by molar masses. So there's carbon and hydrogen and chlorine. Now we're going to, once we find those quotients, 2.02 and 4, this one is also 2.02, divide everything by the smallest, which is 2.02. So we end up with a 1, a 2, and a 1. So our empirical formula is going to be carbon 1, hydrogen 2, chlorine 1. We're going to use that in part B. So we know that the empirical formula is C1H2Cl1. We need to figure out the structural formula. That means that we need to find the molecular mass so that we can find the molecular formula first. We're going to do that with the mass spectrometry. So our greatest value on the mass over charge axis is going to give us the molecular mass. And it's just about 100, 101, somewhere in there. So I'm going to use that mass, and I'm going to find my empirical mass, and then I'm going to use those to find my scale factor. So carbon is 12. I've got 2 hydrogens that are each 1, and chlorine I'm going to round from 35.45 to like 36. Add those all up, 36, 37, 38, 40, 50. So my molar mass for the empirical formula is 50. My molecular mass for the molecular ion on the mass spec is 100. Divide those, we get a scale factor of 2. So I'm going to multiply my empirical formula by 2. C2H4Cl2 is going to be our molecular formula. So to figure out the structure and the name, I need to know which isomer of this guy we're looking at. So there are 2 options. We could have C2H4Cl, where the chlorines were on the same carbon, or we could have C2H4Cl2, where the Cl's were on 2 different carbons. So to figure out which one of these, this one or this one, is our actual structural formula, I'm going to take a gander at the nuclear magnetic resonance signals. So if I'm looking at this first guy, I see that there are going to be 1, 2 hydrogen environments. I've got 1 hydrogen on a carbon with 2 chlorines, and I've got 1, 2, 3 hydrogens on a carbon. So I would have 2 signals in a 1-to-3 ratio. If, however, I've got this guy, then I have 2 hydrogens on a carbon with a chlorine, but these 2 hydrogens are also 2 hydrogens on a carbon with a chlorine. So these 4 guys are actually all in the same environment, which means I would have 1 signal. Since my H1 NMR spectrum is showing me 1, 2 signals, and this guy is just about 3 times as tall as that one, that shows my 1-to-3 ratio, I know that this is in fact my structural formula. I can write it like this on my answer document, or I could write CH3, CHCl2. That would be another way to write the structural formula, and I can name it. Since I have 2 chlorines on carbon number 1, it's going to be 1,1-dichloroethane. Good. All right, last part of question number 1, we are going to polymerize chloroethene. For me, the best thing to do is to draw it. And then I like to think about taking this bond, chunking it in half, and sending it out on either side. So I kind of imagine that I've erased this one, and I'm sending it this way and this way. And then I can draw that polymer. So I'm going to have C to C. I'm going to have H and H and H and Cl. And that's only one a repeating unit. I need 3 of them for my question to be happy. So I'm going to do another CC, HH, HCl. I'm going to do another CC. And you could totally leave your CLs all like that, or you could put one up and one down. Doesn't even matter as long as you have 1 chlorine every one of those 3 repeating units. Make sure that you show those dashes so that we have clear indication that this chain continues. All right, question number 2, looking at bombardier beetles, which spray hydroquinone and hydrogen peroxide to fight off predators. Hydroquinone looks like this. Hydrogen peroxide is here. It's going to turn into these guys. So this is the mass spec for hydroquinone. We need to figure out why this peak exists. Since it seems to be our greatest value, it's probably the molecular ion, but let's find the molecular mass of this guy just to make sure. So I have 6 carbons that are each about 12 plus 4 and 2 more hydrogens is 6 hydrogens that are just about 1 plus 2 oxygens that are 16. And that's going to give me just about 110.12 if I do all the digits. But 110 is a nice rounded number, which just happens to be that peak. So what is the species responsible? We could say that the species responsible is the molecular ion. We could also write it as C6H4OH2. Make sure that you put the sign on that to show that it has been ionized in the mass spec. This next question, same idea, but now we're looking at quinone instead of the hydroquinone. So again, the highest is going to be the molecular ion. But let's make sure just in case. So for this guy, I've got 6 carbons plus 4 hydrogens plus 2 oxygens. And that total molar mass is 108.1 grams per mole. And it looks to me like this guy is just at about 108. And so this species is definitely the molecular ion. That could be an answer. You could also write C6H4O2. Again, throw that plus sign in there to show that we're looking at an ion, not the neutral atom. All right, so here I have a known compound A with empirical formula CH2. That's going to be important in a little bit. So definitely pay attention to things like empirical formulas in the questions. We have mass spec here. What is the molecular mass? We're going to find the greatest value peak, which is 50, 1, 2, 3, 4, 5, 6. 56 is our molar mass. So now that we have that, we need to deduce the formula of the molecular ion. I know that the empirical formula is CH2, which is just about 12 from carbon plus 2, 1 for each of those 2 hydrogens. So 12 plus 1 plus 1, 12 plus 2 is 14. That's the molar mass of the empirical formula. If I divide 56 by 14, I get a scale factor of 4. Which means that our molecular formula is going to be 4 times CH2, C4, H8. Make sure you throw a sign on that because it is asking for the formula of the ion. So now that we know that the molecular formula is C4H8, it's asking us to figure out what even are the fragments that could give rise to peaks at 27 and 29. When I think about hydrocarbons, we know that they're going to be clumps of carbons and clumps of hydrogens. So I like to think of masses of my carbons. If I've got 1, it's 12, 2 is 24, 36, and 48. 1 carbon, 2, 3, 4 carbons. 27 is 24 plus 3. And so I know that this is going to be 2 carbons and 3 hydrogens. What that would look like, carbon, carbon, ooh, if I've only got 3 hydrogens, that's kind of weird because I can't have a methyl group if I have 2 carbons, which probably means that I've got a double bond in there somewhere. So this would be my fragment, which gives rise to peak 27. I could write it like this with the sign, or C2H3 with the plus. 29, I'm going to do the same thing. I know it's between 24 and 36, and so I'm going to go with 2 carbons and 5 hydrogens, because 2 times 12 is 24, plus 5 is 29. So what that would look like is more likely a methyl group. Whoa, those are hydrogens, not carbons. A methyl group, and then another carbon with 2 hydrogens. So C2H5 with a plus is my fragment at 29, and at 27, C2H3 plus. What's nice, even though the question isn't asking us to figure out what the whole molecule is, by putting together these 2 fragments, we could. So I know that I've got a double bond between 2 carbons. This carbon, its valence is full. He's got 1, 2, 3, 4 bonds. I know it's got to be at the end. So I've got this carbon double bonded C, and then I'm just going to chunk the rest of this fragment C. He had an H, he's got 2 H's, he's got 3 H's. So this would be my the structure. So this is going to be 1 meth-eth-prop-bute, 1 butene, not 2 butene, because of the way that these fragments popped apart. If it had been, just a quick gander, if it had been 2 butene, it more likely would have split here, and I would have 2 of the same masses. So we'd have, it would just be a little bit different in terms of those fragment sizes. All right, next one, let's look at this guy. We've got chloroethene. We need 2 features that we would expect to see in mass spec. So the easy thing to think about, I'm going to go ahead and draw it. CHCl. Clearly there's going to be a molecular ion. So I would say that one of the features I would expect to see in the mass spec would be the molecular ion, which is going to have a mass of 2 times 12 carbons plus 4 times 1 hydrogens plus 1 chlorine, which is about 36. So 36, 40, 64. So what about 64? Oh my gosh, that's wrong, because there's only 3 hydrogens. Sorry, 3 hydrogens, 63. So that would be one of the features, one of the peaks that I expect to see on the mass spec. So something else I would expect to see, that chlorine is going to pop off. So I would expect to see that chlorine ion at 36, because chlorine by itself is 36, 35 and a half. And then I expect to see the rest of this guy, 2 carbons and 3 hydrogens, C2H3 would give us 24, 25, 26, 27 is another likely peak. So these are 3 features. It only asks for 2, so we went above and beyond. What would I expect to see in the IR spectrum? So for this, I'm going to look at my table 26, and I'm going to think about the bonds that I have in chloroethene. There's a double bond between carbons. That's going to give me a peak between 1620 and 1680. There are quite a few carbon-hydrogen bonds. Those would give me peaks between 2850 and 3090. And of course, there's the carbon-chlorine bond, which would give us a peak at between 600 and 800. So the question asks for only 2. We have actually listed 3. Again, look at us going above and beyond. Next question. We have the mass spec of iodoethane with 3 prominent peaks, 156, 127, 29. Figure out what those are. So I like to draw. I've got iodine and I've got ethane. So 156 probably is going to be, if it's a prominent peak, my molecular ion, since it's the biggest value, but let's check to make sure. So carbon times 2 is 24, hydrogen 1, 2, 3, 4, 5, and iodine is 156. No, 127. Sorry, 127. And when I add these all up, we do end up then with 156 because iodine. So that's my carbons, my hydrogens, my iodine. Iodine is 127. So 156 is our molecular ion. So our ion responsible for this guy is C2H5. I add the sign to show that it's an ion. 127. I totally just said that iodine was 127. That is the ion that we would see at peak 127. Interestingly, look what we've got here. 24 plus 5 is 29. So this guy is going to be my carbons and my hydrogens. It's going to be the CCHs that are fragmented when the iodine pops off. And so this ion is going to be C2H5 with the plus. So bromine has 2 isotopes of 9 and 81. Now we are asked to think about mass spec for molecules and isotopes all in one. So looking at values that we would expect to see on the mass spec for this guy if I've got 2 isotopes of bromine. So we could have the C2H5Br, where this is Br79. So we'd have 24, 2 times 12 is 24, plus 5 times 1 is 5, plus 79 is going to give us 108, would be C2H5Br plus with isotope 79. We could do it again. 24 plus 5 plus 81 is going to give us 110. That would be the other molecular ion with the heavier of the 2 isotopes. We would have bromine pop off. So we would have that bromine 79 with a mass of 79 and bromine 81 with a mass of 81. So I've got peaks at 108, 110, 79, 81. And the last guy is what happens when the bromine pops off. And I've got C2H5 with that charge because we ionized it in the mass spec machine. 2 times 12 is 24. 24 plus 5 is 29. So another prominent peak would be at 29. All right, question number 6. We're going faster than I thought we would. I've got this guy, C3H6O3, found in human perspiration. We've got the IR spec here on the screen. We need to figure out what bonds are responsible for 1 and 2. So I'm looking here at 1, and I'm looking at my table 26, and I'm trying to figure out what bonds are somewhere between 3,000 and maybe 3,500. And I see that alcohols are at 32 to 3,600. And that's a good match for where this guy is sitting. And so 1 is going to be an OH. So this is my bond responsible for the absorption at Roman numeral 1. 2, it's a little narrower, which sometimes makes it easier to match to the graph. So I've got 15, 16, 17, 18. So we're somewhere between 17 and 1800. I look at my table 26, and lo and behold, 1700 to 1750 is a match for carbon to double bonded oxygen. So the bond responsible for the absorption peak at Roman numeral 2 is going to be carbon double bonded O. For this guy, you could shortcut and just do OH. For this guy, do not do that. Double bonded O, single bond, not the same. Make sure that you show very clearly that this is carbon double bonded oxygen. Good. Here it says that we've got the H1 NMR spectrum for this compound. We have ratios of 1 to 1 to 1 to 3. 1 to 1 to 1 to 3. What does that mean about the peak at D? Well, it means that there are 3 hydrogens in this environment and only 1 in each of those. You could argue, but could it be 6 and 2 and 2 and 2? It could be, except if I go back a screen to the beginning of the question, it does tell us that the molecular formula is C3H6O3. And so C3H6O3, I only have 6 total hydrogens. 1, 2, 3, 4, 5, 6. So deduce what information can be obtained. There are 3 hydrogens in that environment. 3 hydrogens is going to mean a methyl group. So either one of those answers would be correct. You could say that there are 3 hydrogens in this environment, labeled D, or you could say that it's a methyl group. Figure out the fragments that we would see in the mass spec that go along with that guy. So I'm going to go back to our empirical formula, which was C3H6O3. I'm going to look. Since we just have fragments, I don't really have a shape yet. I only have fragment sizes. I'm going to look at table 28. Table 28, mass spectral fragments lost. 45 is at the bottom of my table. It is COOH. It's a carboxyl group. 17 is OH. It's a hydroxyl group. 15 is CH3. It's a methyl group. So sometimes, not always, but sometimes the fastest way to get to those fragment sizes is going to be with that table 28. Doesn't always help, especially if you've got nitrogens and crazy stuff like that. But these, nice and easy to spot. So now I need to deduce the structural formula of X. So I'm going to go back to that C3H6O3, the molecular formula that was given to us in the beginning. And then I'm going to go back here. There are 1, 2, 3, 4 hydrogen environments. So I'm going to jot that down. 4 hydrogen environments. And I'm going to go back a screen. I know that I have a carboxyl group, a hydroxyl group, and a methyl group. So I've got a COOH and an OH and a CH3. So I'm just going to put those guys together. I've got a CH3. I can't put the carboxyl group on yet because it has to be at the end. So I'm going to put that guy on the end. Methyl groups also, since they're 1, 2, 3, they have to be on the end. They can't be in the middle. So what's left to go in the middle? Our hydroxyl group and then that last hydrogen. So I think this is probably the structural formula. Let's double check to make sure that we have a match for our 4 hydrogen environments. I've got 3 hydrogens on this guy. So there's 1. I have 1 hydrogen on a carbon on 2 carbons and a hydroxyl. I have 1 hydrogen on an oxygen and a hydroxyl. And I've got 1 hydrogen on an oxygen in a carboxyl. So I have 1, 1, 1, 3, which is exactly the ratio that we had in our H1 NMR table. So this is our structural formula. It is 1, 2, 3, meth, eth, propanoic acid. I'm going to call it 2-hydroxy propanoic acid. You could leave this as a structural formula, or you could write CH3, CHOH, COOH. This, maybe without the circles, or this would be the correct answer for structural formula. All right, I've got an isomer, which means that it's going to have the same C3H6O3, and it has the same functional groups. So it has a carboxyl group, it has a hydroxyl group, and it has a methyl group. Methyl groups, probably not actually considered functional groups, so ignore that. Deduce the structural formula of Y. I'm going to start with my carboxyl. I know that I've got my 3 carbons. I had hydroxyl in the middle for X. I'm going to put it at the end for Y. Fill in everything else with my hydrogens. Good. And this one does not have a methyl group. Those aren't necessarily considered special functional groups, more just branches. All right. Next part, one difference in the H1 NMR for this guy compared to what we had for Y. For X, this is Y. So in this guy, I've got 1 hydrogen on an oxygen in a carboxyl. I've got a hydrogen on an oxygen in a hydroxyl. And then I have, it looks like these 4 hydrogens might be in the same environment, but they're not quite, because this carbon is stuck to 2 carbons, whereas this carbon is stuck to a carbon and an oxygen. And so this, what's going on over here is going to make these guys a slightly different environment. So I'm going to have 1, 2, 2, 1 for my ratios, whereas the other guy, X, had 1, 1, 1, 3. So that would be the difference that we would see. So 1, 1, 1, 3 was the ratio for X. 1, 2, 2, 1, or 1, 1, 2, 2, or 2, 2, 1, 1 would be the H1 NMR spectrum for Y. So this guy, 3-methylbutanoic acid, is also a source of body odor. We're going to figure out the molecular ion. This just means what's the molecular mass. So I am going to draw methylproputanoic acid, 3-methyl. So there's carbon 1, 2, 3, gets a methyl group, hydrogen, 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 hydrogen. Remember that carbon has a valence of 4. It always needs 4 bonds. So I'm going to add this up. I've got C4H, 1, 2, 3, 4, 5, 6, 7, 8, 9. Oh gosh, C5. Sorry, I missed that methyl group. 1, 2, 3, 4, 5 carbons. Hydrogens, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Oxygens, 1, 2, C5H10O2. 5 times 12 is 60, plus 10 is 70. 70 plus 2 times 16 is 32 is going to give me a mass over charge. M over Z value for the molecular ion will be 102 when he's an ion. How many different environments would we see for the H1 NMR of this guy? So I've got these 3 hydrogens in a methyl group on this carbon. This carbon also has these 3 hydrogens in a methyl group. So these guys are in the same environment. I've got 6 hydrogens in this environment. I have 1 hydrogen on a carbon on 2 methyl groups and a carbon. I've got 2 hydrogens on this carbon, and I've got this hydrogen on this oxygen. So how many different environments? We're going to have 1, 2, 3, 4 environments. And if it asked us for the ratios, it would be 1, 2, 1, 6. Last question. All right, so I've got 3 isomers of C3H6O2, 1, 2, 3. This is asking us to figure out which of the 3 is going to have peaks at this and that. So I'm going to start with the molecular mass. So C times 3, carbon times 3 is 36, plus 6 hydrogens plus 32 is going to give me 60, 72, 73, 74 is our molar mass. 74 minus 59 is going to be 15, which I happen to know is CH3. So I definitely want something that has a methyl group, and interestingly, they all have methyl groups. So that's not so much a help. But what about this 44? So if I take off, so if we do 79 minus 44, I have a mass of 30, which could be 2 methyl groups. Is there anything with 2 methyl groups? You might be tempted to say, well, yes, they all have 2 methyl groups. 1, 2. But this guy only has 2 hydrogens, not 3. If we look at this guy, I've got 1 methyl group, I've got 2 methyl groups. So if I were to add the mass of COO, 12 plus 16 is in fact 44. So this peak at 44 is going to be this middle guy, carbon, oxygen, oxygen, after the 2 methyl groups are blasted off the ends. And then the 59 is going to be, if I chopped off only one of the methyl groups, chop, and he flew off, what's left? I have 16, 16, 32 plus 12 is 44, plus 12 is 56, 57, 58, 59. So the mass of this chunk is 59. So we definitely have methyl ethanoate as the compound with the mass spec of those peaks. And that's all I've got for mass spec. Hopefully this wasn't too terribly boring and long. Hopefully it was a help. More videos coming soon.